Hi, my name is Tom Heffel. This channel is all about helping students learn chemistry. In this video, we're going to be talking about voltaic, and sometimes called galvanic, cells, which are like batteries. And voltaic and galvanic cells only works when you have a spontaneous reaction. And the word spontaneous just means thermodynamically favorable, or that it will occur. And the chemical reaction that we're going to talk about today is when I place zinc in a solution of copper sulfate. Now, I have some test tubes here, okay? And what I have is basically, here's the piece of zinc. Now, if I put the zinc directly into water, zinc metal does not dissolve, okay? So let me try to get you to see this a little bit better. I got a little background here, so maybe something like that. So zinc metal on its own, it's not going to dissolve, and it's going to remain as a solid, okay? Now, copper sulfate, it does dissolve in water, okay? So you're going to get that blue solution, okay? And those copper and sulfate ions are going to split up, okay, when they dissolve in water. So this next equation down here is kind of like what we call a complete ionic equation, where the copper and sulfate are separated. Now, if I mix those two together, if I take this piece of zinc that's a solid and place it into the copper sulfate solution, okay, you're going to get this to occur, okay? And this is going to be zinc sulfate solution. As you can see, there's no color here because it's zinc sulfate solution, doesn't have color. The copper sulfate solution was the blue color, just for reference, okay? And I don't know if you're going to be able to see it on the very bottom here, but you're going to get this like orange-brown color, and that orange-brown color is going to be the copper solid that's being made, okay? So obviously through this series of test tubes where we have just the zinc, the copper sulfate, and then when you mix them together, obviously you have no blue color there. So we got the zinc sulfate solution in copper metal instead of zinc metal here at the bottom. So we know that this chemical reaction does occur. So we say that this is a spontaneous reaction because it's occurring naturally. And what we're going to do is we're going to take this complete ionic equation and turn it into a net ionic equation by canceling out any spectator ions. So what I'm looking for is something that's the same on both sides. Now, on this side, the zinc is neutral, so I'm going to put a 0 there. And on the right-hand side, zinc is positive 2. This is when it's a metal, and this is when it's dissolved in solution, okay? Same thing for the copper ions. Over here, it's in solution, okay? That gives me that blue color. But on the right-hand side, it's going to give me that orange-brown color for a solid metal, and it's neutral. So these are not the same thing. In fact, the only thing that's the same is going to be the sulfate ions. And the sulfate ions are called spectator ions. They're just watching this reaction occur that's happening between the zinc and the copper ions. And what we're going to realize is that if we investigate this reaction a little bit more, that it ends up being an oxidation reduction reaction. So these spontaneous reactions, they have to be a special type, okay? And they're going to be what we call, in short, a redox reaction, which just simply stands for oxidation and reduction kind of put together. So we have a redox reaction where one thing is being oxidized and the other thing's being reduced. So let's kind of write some half reactions, just like we did in our lesson a couple days ago, on how to write the half reactions for oxidation and for reduction. Now remember, for oxidation, this is the thing that's going to go up in oxidation number. In this case, it's going to be the zinc. It's going from 0 to positive 2. So if the zinc goes from 0 to positive 2, 2 electrons are going to be released. So if you have neutral zinc and you pull off 2 electrons, there they are, you're also going to end up with a zinc ion, okay? And zinc ions have no color, okay? For reduction, we have the copper ions that do have color. This is your blue color. Those copper ions are going to take 2 electrons, and that will end up forming the copper that's neutral. So in this case, the zinc is being oxidized. It's giving up 2 electrons, and the copper is being reduced. It's taking those 2 electrons, And when they take the 2 electrons, the oxidation number goes down. In this case, it's also the charge. Okay? So the goal of a voltaic or galvanic cell is to take advantage of this electron transfer where one thing is giving them up and the other one is taking it in. If we're able to separate them into compartments, then the electrons are going to flow along this wire and we can take advantage of that flow of electrons because that's basically what electricity is that powers our cell phones or anything else that has a battery in it. So we're going to talk about the general parts of a voltaic or galvanic cell, and every cell is going to have something called an anode compartment that contains a strip of metal called the anode, and then the same thing is true in the cathode compartment. Okay, the cathode compartment is going to hold a strip of metal called the cathode. Okay, now I have a mnemonic to decide which reaction is taking place in which compartment, okay? And it's just to match up your vowels with your vowels with the vowels and your consonants with the consonants. What do I mean by that? Well, oxidation has a vowel in it, so wherever you have oxidation, that's going to be in your anode compartment because both of these are vowels. And then the same thing is going to be true for reduction. That's going to take place in the cathode compartment. An R and a C are both consonants. So you match up the consonants and you match up the vowels. So over here where I have the anode compartment, okay, the anode compartment is going to have our oxidation. So I'm going to copy this reaction right below the anode compartment, and that's going to be the zinc metal turning into zinc ions in solution and releasing 2 electrons, okay? So I'm just going to put an S here for solid and AQ for aqueous because whenever it's an ion, it's going to be aqueous. So what is happening specifically here is that we have a strip of metal, and that strip of metal is going to be zinc. Zinc is going to be in our anode. It's going to be the electrode, and then that electrode's called the anode if it's placed in the anode compartment. Now, inside here is going to be a solution that contains these ions, okay? Now, the solution that we're going to use here is we're going to pair the zinc ion with a negative ion that is always soluble. So that can be either nitrates or acetates. Nitrates are a little bit easier to write, okay? So I'm going to go ahead and put some zinc nitrate solution here. And when that dissolves in water, you're going to have zinc ions. And for every 1 zinc ion, you're going to have 2 nitrate ions. So I'm trying to make a particulate diagram by showing this chemical reaction. Okay. Now what's happening in the chemical reaction in this anode compartment is that the zinc metal, that's neutral, is turning into zinc ions. So something like this. This zinc is being consumed. So I'm going to kind of eat it out a little bit here, remove a piece of that. And that zinc metal is then going to make more zinc ions. That's the chemical reaction that's taking place at the anode. And one of the common questions that's usually asked is, what's happening to the mass of the anode? Well, if zinc metal is being consumed to create zinc ions in solution, then the anode's mass is being decreased as this chemical reaction takes place. It's a reactant, okay? The zinc is being consumed and it's producing the stuff that's on the right-hand side of the chemical reaction, okay? Now, let's do the same thing, but for the cathode compartment. So I'm going to take this reaction right here where it's copper ions taking in a couple electrons and making some copper metal. So I'm going to put AQ for the ions and S for the solid copper, okay? And so we know that this electrode is going to be copper metal, okay, because that's where the copper's at, okay, and it's going to contain ions of copper. And once again, copper's a positive ion, so we have to pair it with a negative ion that is always soluble. So I could use nitrates or acetates. I'm just going to use nitrates again. So I'm going to put it in a solution of copper nitrate. And for every 1 copper ion, you're going to have 2 nitrate ions. Now what's happening over here is that the copper ions are receiving electrons, okay, and it's going to make copper metal. So these copper ions are going to take electrons, and what's going to happen is that we're going to start to plate out some copper metal right on top of the existing copper metal that was already there. So let's summarize both parts, okay? Zinc is changing into zinc ions, and when it does it, it releases 2 electrons. Those electrons are traveling through the wire to go into the other compartment. And when that compartment accepts the electrons, the 2 electrons, the copper ions are making more copper metal that's being plated on the copper metal that already exists. And this is kind of how we take advantage of electron transfer, because now we have these electrons traveling through a wire, and if we hook up some type of electrical component to this, we can get it to operate. Maybe your watch, maybe your cell phone, etc. So we want to figure out, well, how much, what's the potential between these two metals? Like, what kind of voltage are we going to get out of a battery that's constructed this way? Okay. Well, in most books in the appendix, there is a sheet that looks something like this, and it's called standard reduction potentials. Okay. And the way you calculate the standard reduction potential for a voltaic or galvanic cell is you're going to take the variable for it is going to be E naught cell, and we'll come back and talk about that. But basically, we're going to take the cathodes reduction, and we're going to subtract away the anodes reduction, okay? Because this sheet is only reductions, and we know that at oxidation doesn't go through reduction, only at the cathode it goes reduction. That's what this subtraction sign is all about, and saying, hey, we don't want reduction, we want the opposite of reduction, which is going to be oxidation. But what I'm going to do is I'm going to look up these two values on my sheet, and I circled them here, and you're going to find out that the copper is at 0.34, okay, so we got 0.34 volts here, and for the zinc is negative 0.76 volts. And what we're going to do to figure out the cell potential is we got to take the cathode, which is 0.34, and we're going to subtract away the anode compartment, okay, which is negative 0.76 volts. And when you do that math, you're going to find out that this battery is 1.10 volts. So if we had something that was measuring the potential between these two metals, it would read 1.10 volts. Okay, now your AA batteries and your AAA batteries, they're about 1.5 volts, so they must be using different metals inside, or maybe manipulating some other variables to get the potential up to 1.5. But this is not a bad battery. It's at 1.1 volt, okay? And so this is how you calculate what we call cell potential, okay? So this is called cell potential. Sometimes it's called cell EMF, which stands for electromotive force. So sometimes it's called that, and I've heard kids just call it voltage, but really voltage is the units, okay, for the potential that exists between our anode and cathode, okay? So cell potential, cell EMF, or E-cell, all those things kind of mean the same exact thing. Now, this circle right here stands for a standard state, okay? And for our standard state for us, okay, it means that this reaction is going to occur at 25 degrees Celsius, okay? It also tells us that the solution molarities, okay, have to be 1 molar. If these solutions are no longer 1 molar, then the values on our list are no longer true. So we have to make sure that the molarity here is going to be 1 molar. In fact, if it ever changes, then you'd have to use the Nernst equation, and that's going to be a lesson in a few days. So for right now, we're talking about things in their standard state, 1 molar solution at 25 degrees Celsius in order to calculate their cell potential. Now, the one thing that's missing from our battery to finish it up is what we call the salt bridge. Because as you can see, the electrons are just traveling in this direction. Well, for a circuit to be complete, you have to complete it. And the salt bridge, that's one of its main functions, is to kind of complete the circuit. So what we're going to do is we're going to connect it with some type of gel. Sometimes it's an ionic compound, okay? And the big thing in our ionic compound that we have in here is that it will not form a precipitate. So we do not want any precipitates forming on our salt bridge, because precipitates are really, really bad for batteries. We try to avoid them at all costs. So for the positive ions, I'm going to pick something that is always soluble, okay? And that's any alkali metal. Anything that's in group 1 will be perfect for a salt bridge, followed by nitrate, okay? I really like nitrates because they're easy to write, but I could also have done potassium acetate. That would have been fine. Anything that is always soluble will work, okay? Now, the ions of potassium nitrate are going to migrate in a particular direction, okay? If you look over here, we're constantly consuming positive ions. I'm not consuming positive ions. I'm sorry, producing positive ions. The zinc metal is making positive ions. So this compartment's getting very, very positive. So that's not going to really attract more positive ions. In fact, it's going to do the exact opposite. Positive compartment's actually going to attract the nitrate ions, which are negative. So what we're going to find out is that the nitrate ions, which are negative, are going to flow towards this compartment in order to try to maintain its neutrality. And the opposite is true over here. Over here, all the positive ions are being consumed. So this compartment's getting very, very negative unless the potassium ions start to migrate towards the cathode compartment. So the salt bridge has 2 functions. Number 1, it completes the circuit, okay? And then number 2, it's going to try to maintain neutrality in each of the compartments by having particular ions migrate to the compartment to, like, the one that's producing all the positive ions is going to attract the negative ion. The one where all the positive ions are being consumed and it's becoming negative will attract the positive ions because of the opposite attract or Coulombic laws that exist, okay? And then finally, really the last thing that we need to talk about here is something called cell notation. And our cell notation looks something similar to this. Okay, let me get my notes out here. Sorry about that. Okay, so for our cell notation, it's going to look like this. Of course, I'm going to explain it after I have everything written down. And what this stands for is the first part is going to be whatever our anode is. In this case, our anode is zinc. And then this is going to be the anode compartment. And remember, the anode compartment is going to contain that same solution. So we got a whole bunch of zinc ions. And because it's under standard state, the molarity is going to be 1 molar. Okay, if you ever go a different from something other than 1 molar, you would have to list it after here after we write down the anode compartment. The double line is actually the representation for the salt bridge. Okay, and then we have the cathode compartment with the molarity that exists in the cathode compartment. Since we're standard state, we're still at 1 molar. Okay, and then followed by the cathode. Okay, so really this little statement represents everything that I have on the board up here. Okay, and one last thing that I like to include, in a voltaic or galvanic cell, there are some signs for the anode and cathode. And the cathode is going to have a positive sign because it's attracting the electrons, okay? And the anode is going to have the negative side because it's kind of like releasing all of the electrons. If you want a mnemonic device for that as well, the word cathode kind of has a T in it, and it kind of looks like a positive sign. And remember, that is for voltaic or galvanic cells, which have spontaneous reactions that occur naturally in a particular direction. Now, as we move forward, we're going to talk about different types of cells, okay? The next type of cell that we're going to talk about is concentration cells, and that's when it's no longer in its standard state, when the molarities are going to change, and we call those concentration cells, okay? And then finally, we're going to talk about electrolytic cells, and that's going to be when we have non-spontaneous reactions, which are basically like this reaction in the reverse direction would be non-spontaneous. And the only way that I would be able to push electrons this way is if I plugged it into an outlet or an external power source that would push the electrons in a direction in which they don't want to go. Because between zinc and copper, according to this list, okay, they like to flow only in this direction naturally, okay? So there's going to be some different words out there for different types of cells. The ones that we're doing today is how it occurs naturally, and those are going to be our voltaic cells, okay? The electrolytic cells is when we force the reaction to occur in a different direction, okay? And then finally, our concentration cells is when the concentration is something other than 1 molar. If you found this information helpful, please give it a like and subscribe. When you add that comment, it really does push this information out to other students that are interested in learning chemistry.